Assalamu alaikum and good morning. Today we're going to continue with our topic 5, chemical energetics. So we've looked at drawing Hess cycle to work out the unknown enthalpy change of reaction. So based on Hess's law, it says that if we cannot find the enthalpy change of a reaction directly, we can always use an alternative route. Okay, so moving on with example number 5, it says that estimate the bond enthalpy change for the reaction. So the key word here is estimation. There is no other enthalpy change values that are given to us. And we know that we can find enthalpy change from bond energy values. And if you remember that I've mentioned that bond energy values are average. Okay, so it even mentioned it in the data booklet. So when the question says estimation and there's also no other values given to you, then it means the question wants you to work out using the bond energies or bond enthalpies value. Okay, so with bond energy values, we need to know the bonds that are present in each reactant and product. So the best way to do this is to draw it out. Okay, in the exam, you can just start straight away with counting the number of bonds, the type of bonds, and then, just take the formula total bond energy of reactants minus total bond energy of products, or you could, and it's always the safest, draw out the molecule. Okay, so C2H4 is an alkene, and good thing that they are in gas state, because bond energy, the definition of bond energy is the energy taken in when 1 mole of bond is being broken into atoms in gas state. So everything must be in gas state. Okay, and then I'll just label this your reactants. And then we've got water. And make sure you also look out for the number of stoichiometry, the mole ratio in the equation. Okay, so in this case, they're just 1 mole. Okay, now this is where I'm going to let you finish off the question, but I'll help you with counting the number of bonds first. Okay, so in ethene, we've got 1 times C double bond C. Okay, and then we've also got 4 times C double bond H. So please use your data booklet to find the values of C double bond C, which is 610, and CH, which is 410. But don't forget, because there are 4 of them, 1, 2, 3, and 4, you multiply it by 4. Okay, I'll leave you guys to work out the actual numbers and the addition of all the bonds that are present in the reactants. As for water, there are 2 times OH bonds. Okay, so you total up all the bond energies for your reactants, and then you do the same for your products. So you've got an alcohol, and this is CH3, an ethanol. If you can visualize it, that's great. You're at an advantage. But if you tend to make mistake, safest for you to draw it out quickly. Okay, so I'll start with CH bonds. There are 1, 2, 3, 4, 5 CH bonds in my ethanol. Sorry, there's only 1 product, so I'll omit the S. And then there is a C single bond C. Now it is important for you to identify the correct type of carbon-carbon bond. Okay, just because they are carbon with carbon, they will give you different values. So a single carbon-carbon bond will be 350, and a double carbon-carbon bond will be 610, and that will affect your calculation and will result in getting wrong answer. Okay, so my CH bonds are done, CC bonds are done. There's a CO, there's only one of them, and there's an OH bond. Okay, so you list out the numbers and then you work out the sum and use the formula delta H is equals to sum of your energy bond enthalpy of reactants minus the sum of your bond energy of products. So with bond energy, you can easily use the formula and you will always almost get it right. But I don't recommend you to use the formula when working out using the enthalpy change of formation or the enthalpy change of combustion. Okay, so please work that out and then write down the answer. You will key in this answer into the Microsoft Forms later on. Okay, next is example 6. Calculate the standard enthalpy change for the formation of solid ammonium chloride. So that means we are required to work out the delta HF of solid ammonium chloride. Okay, so the formula is given NH4Cl and it is in solid state. Okay, these are the given equations and values. So usually our enthalpy change of reaction here is our unknown. This is our X. Okay, but this time it's given to us, which is negative 176 kilojoules per mole. And then we are given enthalpy change formation of ammonia and enthalpy change of formation of HCl with its respective values in kilojoules per mole. So whenever you're given like a value, I always tell you, and the first step is to write down the equation that corresponds to the definition. Okay, so let's start. Enthalpy change of formation of ammonia by definition is when you form 1 mole of ammonia gas from elements in its standard state. So if you go through the formula of ammonia, there is a nitrogen, and nitrogen exists as a diatomic molecule, N2, and there is also a hydrogen in the formula, and it exists as a diatomic hydrogen molecule, H2. And you need 3/2, 3/2 to balance this equation. Okay, so this is the enthalpy change of formation of ammonia, and I will call this equation A, okay, as usual. And then the next enthalpy change of formation given is of HCl, same thing. I need 1 mole of HCl gas from elements in its standard state. So going through the formula, there is an element hydrogen. Hydrogen in its standard state is a diatomic molecule, so I should write it as H2. And chlorine is also a diatomic molecule, hence Cl2. Now, my HCl has to be 1 mole because that is the definition. So I have to change the number of moles, the mole ratio of my hydrogen and chlorine gas in order to accommodate for the formation of 1 mole of hydrogen chloride gas. So that means I need half hydrogen and half chlorine. Okay, so I've got 3 equations here. HR naught, that's my enthalpy change of reaction. I've got reaction A, which is equation A, and equation B. Okay, so there is no strict rule that says the unknown has to be at the top equation. Okay, I like to keep my enthalpy change of reaction on top, whether there is a value for it or whether there is an unknown X for it, okay? But before that, can I just, for the sake of following the question, can I just write down the equation for ammonium chloride, which is our X, okay? So this at the moment is our X, and by definition, enthalpy change of formation of ammonium chloride is 1 mole of NH4Cl solid is formed from nitrogen N2 plus hydrogen H2 and chlorine Cl2. Okay, so I'll just move it a bit so I can make space for the mole ratio. Okay, nitrogen, I need half. Hydrogen, I need 2 moles, and chlorine, I need half. Okay, and this is my equation X, and this is what I'm going to find out. Right, I will start with enthalpy change of reaction to be on top. So now we move on to step 2. My step 1 is done. This is step 1 where I write down all the relevant equations. Step 2 is my drawing of Hasse cycle. I will start with, I will leave out the state symbol because I've already sorted out the equation. Okay, you can edit if you want, but in the exam, I don't think you will have enough time, or you would remember to do this. Okay, all right, so that is my delta HR, which has a number, but I'll just label it as delta HR for now. Moving on to my equation A, I need to put my equation A in a Hasse cycle, and Hasse cycle has a format of an inverted triangle, okay? So the top one is reactants to products, and then the 2 arrows can be going down or going up, okay? So that's what we're going to work out here. Now, if you look at equation A, and you can see that there is NH3 and also NH3 here in the equation for delta HR. Okay, so if I want to place equation A, I would take nitrogen gas plus 3/2 hydrogen gas to form NH3. And it turns out that I'm forming 1 mole of NH3. I repeat, if you look back at equation A, when 1 mole of nitrogen reacts with 3/2 moles of hydrogen, it forms 1 mole of NH3, and this is represented by reaction A or equation A. Next, B is I need half hydrogen. So I'm going to use B plus half hydrogen gas plus half Cl2 gas. I should have moved this so that it doesn't look funny later on. Okay, just to make it in the middle. Okay, so equation B says that half hydrogen gas react with half chlorine gas to form 1 mole of hydrogen chloride gas, and that is equation B, right? You have to make sure that the arrow is correct. If we're talking about enthalpy change of formation, then it has to be from the elements to the product. Okay, now notice that we can combine the 3/2 hydrogen plus 1/2 hydrogen. So this can be, well, this is basically just 2 moles of hydrogen gas. Okay, you can simplify it. Next is our X. Can you see that NH4Cl, ammonium chloride, is the same term as the ammonium chloride on the enthalpy change of reaction, which is in the black colored, which is in the black writing. Okay, it's the black colored equation. So if you look on the Hasse cycle and you compare it to the equation of X, okay? What's wrong with my nitrogen here? Ah, I spotted. I forgot to balance it. This should be half, okay? Right, now back to my equation X. Half nitrogen plus 2 hydrogen, which is the total, okay? Plus half chlorine is equals to NH4Cl. So that means my third equation, it's lagging, okay, is represented by X. All right. So now it's really slow. Okay, so please make sure, yeah, I forgot to balance the nitrogen here just now in equation A, which is supposed to be half nitrogen instead of 1 nitrogen. Okay, so you will notice that there will be a delay in my writing compared to the audio because the connection is really slow right now. Okay, next is step 3. Now I will leave step 3 for you to do. Step 3 is when you equate root 1 equals to root 2. So this is where you put in your knowledge of vectors into play. So you have to be careful with it, okay? Now, just before I leave this question, I just want you to make sure that you've checked all the mole ratio or the stoichiometry numbers, just in case that sometimes you may need to multiply your enthalpy change values. But in this case, they're all 1-to-1, so it's not a problem. Let me just add in the labels, okay? A is represented by delta HF of ammonia. Equation B is delta HF of HCl. Equation X is what we're going to find, which is delta HF of ammonium chloride. And HR, there is no specific name for the enthalpy change of the reaction that we have, the reaction between ammonia and hydrogen chloride gas to form ammonium chloride solid. But remember, delta HR is represented by -176. So usually we have our top equation to be the unknown. It usually has the value of X, okay? But this time you know the value of the top equation. So it shouldn't change much, okay? As long as you follow the vectors, okay? If you want to find X, what's the root that you have to follow, okay? So work this out, and the answer, please write down your answer, and then later on you put it in, submit to the questionnaire in forms. Next question is example 7. Calculate the enthalpy change of formation of methanoic acid from the following changes of combustion. So they give us the value for enthalpy change of combustion, hydrogen, carbon, and HCOOH. That's fine. We can work out the equation for that, equation ABC. The main question is the formation of methanoic acid. So that is the X that we want to find. And you notice that they didn't give the equation for us, but it's not the end of the world because you have already learned the definition of enthalpy change of formation. So you should be able to write it down, okay? I think I will just quickly write down the enthalpy change of formation of methanoic acid. Delta, I'll use black for that since that will be my top equation. Delta HF of methanoic acid, even the formula is not given to you, okay? So you have to be careful. That's why definition is important here, and naming of your compounds, not just your organic compounds, but also your inorganic compounds. It's important. Methanoic acid is a carboxylic acid with 1 carbon. So if you don't remember, you can always draw it out. Okay, so that's methanoic acid, HCOOH. And that is the value that we want to find. So I will label it X. And the equation that corresponds with that is, by definition, I form 1 mole of methanoic acid. Methanoic acid, I believe, would be a liquid at room temperature. And then from elements in its standard state. So I've got a hydrogen, which exists as a diatomic molecule, carbon, which exists as a solid, and oxygen, which exists as a diatomic molecule. And the next thing I need to do is just balance, and it balanced out nicely. Okay, so I've got 2 hydrogen, I've got 1 carbon and 2 oxygen. Okay, so that's my equation for X. Next, I would want to write down the enthalpy change of combustion of hydrogen. By definition of combustion is when we burn 1 mole of the substance, whatever substance that is in the bracket, that is the substance that we're going to burn, okay? 1 mole of hydrogen gas is combusted in excess oxygen. Sometimes with combustion reaction, you kind of have to guess the products, okay? So hydrogen and oxygen, you would expect it to produce water, H2O. Okay, so for this one, do I want to write down H2O? Would be most likely to be liquid. Okay, next thing to do is balance. My hydrogen is balanced. Well, my hydrogen has to be 1, okay, because it's 1 mole of hydrogen burnt. Oxygen would have to be half to balance the H2O. Okay, that is equation A, and equation A has a value of -286. Next is the enthalpy change of combustion of carbon. So that means I am burning 1 mole of carbon solid in excess oxygen gas to form, again, carbon plus oxygen, you would expect carbon dioxide gas. So I can change the number of carbons, so automatically I cannot change the number of moles of my products. So the next thing to do is just to balance the number of moles of oxygen, and it happens to be balanced. Okay. Again, it's slow. Yeah, so 1 mole of oxygen, and this is now equation B, and equation B has a value of -394 kilojoules per mole. And lastly is the enthalpy change of combustion of methanoic acid. So that means I combust 1 mole of HCOOH liquid in excess oxygen gas to form. Okay, so this is an organic molecules with oxygen. It's a combustion reaction. So a typical combustion products for a hydrocarbon or organic molecules would be carbon dioxide and water. Still nothing too difficult. Okay, the next thing to do is you have to balance. And I believe that your hydrogen is balanced, your carbon is balanced. So you've got 1 carbon, you've got 2 hydrogens, and you've also got 2 hydrogens. The next thing to do is to balance your oxygen. I've got 3 oxygens on the product side. That means 3/2 oxygen of gas is needed. And this is labeled as equation C, and I know the value of equation. Oh, before I forget, you need to change the value of equation C because that is a typo. in example 7, please change that to negative 263 instead of negative 890. Okay, so my step 1 is done. Next, I move on to step 2. So step 2, I have to arrange them in Hasse cycle. Again, I like to put my enthalpy change of reaction on top. In this case, it happens to be unknown, so it's my X. H2 plus carbon plus oxygen to form HCOOH. And conveniently, they're all in 1 mole. Okay, next step is to put in my equation A. So if you go through equation A, there's hydrogen, there's oxygen, and H2O. So there's not really an H2O here, but because we're talking about the combustion of hydrogen gas, and you can see that there's a hydrogen here. So that means this time I have to do this, okay? Hydrogen plus half oxygen. So that means I have half remaining to form. That means to form would be going down. H2O liquid, okay? So that's equation A, done. Next is equation B. 1 carbon reacts with 1 oxygen. Now notice that I have already used half oxygen just now for equation A. So I'm left with I'm left with half oxygen. Okay, so that means I need another half oxygen plus half oxygen. Okay, so that oxygen, just leave it there for now because later on hopefully it will cancel out to form carbon dioxide. So I don't have carbon dioxide yet, so I'll add in carbon dioxide, which is in gas state. And this is represented by equation B. Now, do you notice that we did not have a value, or we didn't write the equation for the combustion of oxygen, okay? Now, if you burn oxygen in itself, you will just forming oxygen. You will just be forming oxygen. You're not forming anything new, okay? So just for argument's sake, okay, when you combust oxygen, the value is 0, okay? So delta HC of oxygen, you can actually leave that out, right? It's up to you whether you want to write this in or you leave it out. Next, we move on. So B is done. Next, we move on to C. Again, if you compare to the equation of C, HCOOH plus 3/2 O2, since I don't have any oxygen on the product side, to form CO2 and H2O. So that's nice. I don't have to write it 2 times, okay? Actually, if you notice, the number of products here should match with the number of moles of your reactants, okay, separately, and then the number of moles of your products separately. So you don't have to keep on adding, oh, my HCOOH is producing CO2 and producing H2O again, so I have to add them on. No, okay? So just see it as like this. HCOOH will produce H2O plus CO2. So my equation C will give out 1 mole of CO2 and 1 mole of H2O. Whereas on the reactant side, my equation A and equation B should give out in total, 1 H2O plus 1 CO2, okay? All right, so what else? I want to move this here so that it looks nice to be in the middle. And that's my equation C done. So I'm left with just labeling. The top equation is my equation X, and that's my unknown. Equation A is the enthalpy change of combustion of H2. Now you notice that I tend to leave out my standard state symbol, okay? That doesn't mean that it's not under standard condition. It is still under standard condition. It's just that I just leave it out so that it's quicker for me to write things down. B is enthalpy change of combustion of carbon. Oxygen is, this equation here can be omitted because it's just 0, okay? So to not confuse you guys, I will omit that. Next is my C, which I haven't labeled. C is actually my delta HF COOH. Okay, so be careful with the values that I just changed here. So that's done. Check that everything is in 1 mole. So I'm burning 1 mole of hydrogen to form water. I'm burning 1 mole of carbon to form CO2. I'm burning 1 mole of methanoic acid to form 1 mole of H2O and 1 mole of CO2. So that brings me to step 3, which you will again work out yourself. Okay. Next would be example 8 and 9. What do we say? Do we want to write that down together? Okay, so I think I will let you try example 5, 6, and 7 first, okay? Using the hints that I have given you, and then in the next lesson, I will give you the answer. Actually, why don't I just give you the answer now? Example 8, the answer is delta HF, it's combustion. Delta HR of C2H4 is -1412 kilojoules per mole. And then example 9, which is the last question, it wants you to find the the heat of the reaction. So delta HR, just delta HR, because there's no specific name for that reaction, is -184 kilojoules per mole. Okay, so we'll work through example 8 and example 9. Just let me know if you can get the numerical answers or not, and we'll see how it goes. If a lot of people cannot get the numerical answers for example 8 and 9, then I will show you the working to these 2 questions. Okay, so for example 5, 6, and 7, I've already given you on how to start these questions, and all you have to do is just equate the 2 roots. Okay, root 1 is equals to root 2, and then you can key in your answer in the Microsoft Forms and check if you get the correct answer or not. Okay, all right, Assalamu alaikum, and thank you very much.